stop the timer. So this is a question about peppers, but actually it's a question about intersection and union. And we have these two sets of peppers. So this curly bracket over here, I don't know if we talked about curly brackets last time. This is in math. We sometimes use curly brackets to mean, look, I'm thinking of a collection of things, a set. So R equals curly bracket something means R is a set. And in this case, it is the set consisting of P1 and P2. So R is the collection of the first two peppers, P1 and P2. Those are the red peppers, the peppers with red on them. And G is P2, P3. Again, curly brackets to mean a set of things. And that is the collection of the green peppers. And then the question is, when someone says, please chop up all the red peppers and green peppers, what do they mean? And it could be a union or an intersection. You might remember from last class, we talked about union and intersection, and the definitions have something to do with and or, but which one is which? Let's see what you guys said. Okay, hoo-hoo, very evenly split, 31 to 34. This is a good chance. This means something is unclear about the definition. I will give you a chance to revote in a second, but before I give you a chance to revote, first thing, let me remind you, so your homework due next Friday is all about these definitions, so that will be your chance to learn about the symbols. I also made a little bit of a, so this is the course website, or my website with some stuff, and this is sort of like a dictionary page with all of the special words that we learned last class that we'll use in the course. So some of them, I guess let me tell you about this. It's a little bit like a Wikipedia page. So there's, over here is some different courses. So you want to be in Introduction to Probability. Introduction to Data Science is the other course I'm teaching. There's some other things. Oh, this is a good one. This is night mode. You can do night mode. It should work on your phone as well. And there's a link on the website. And down here is a list of all the things. So you can also quickly flip to the things you want. And this has a little definition of all the things like we learned about last time, like sample space, the letter S. And here's the example with the dice. These are two four-sided dice, and so on. We are interested in intersection and union. So I'm going to click on intersection here. And this is the intersection symbol. And this I got from Wikipedia is a picture of what an intersection means. It's the set of things that satisfy both conditions. So you satisfy condition 1 and you satisfy condition 2. That is an intersection. And a union is this kind of picture. And that is with an or. So you satisfy condition 1 or you satisfy condition 2 or both. This is important. Or in math class always is an inclusive or that includes satisfying both. So that's intersection and union in pictures. That maybe is a hint for you on what is going on. I'm going to open the MathMatize problem again, and feel free to talk to your neighbors this time. Let's see if we can reach a consensus just based on the little hints I gave. What is the actual answer? OK, feel free to go talk. I'm going to run this again, and we'll reconvene in a minute. OK, so time is up. So what happened? We voted the first time, and it was pretty split between the union and the intersection, which is the upside down U. I gave you a hint in those pictures from before, and then I said, you guys discuss and see if you can figure out the right answer. Let's see what you said this time. All right, so big shift. Before it was split pretty 50-50, and now is a big majority on the union, And if you remember, the union is the one with or. So if I go to the definition, it says union, also known as or, and it has this U symbol, and it is the thing of red or green or both. And this is very confusing to some people, because if you read the question, it says the word and. Please chop up all the red peppers and all the green peppers. So you guys all said union, which is or, and then the question says and. But nevertheless, you guys are all right. So very good job, people who selected union or who figured out that it was union or who explained it to your neighbor. Great work. And the whole point of this question is to show you that the union, even though it's defined with or, in real life, in English language, sometimes the word and actually means a union. And that's because this and was not the and on the conditions, right? So this is the thing that is the difference. This is telling me to do two tasks. First, cut up all the red peppers. And then, when you are finished, cut up all the green peppers. So this is do two different tasks. The or in the union is the conditions, right? Does it satisfy being red or does it satisfy being green? And so the and in the English language was like a list of things, do this and then do this. And the or over here is conditions. Which conditions does it satisfy? And that is why sometimes an and seems like an or. It's because the word and is overloaded in the English language. It can be used for many different things. An intersection in probability and in set theory means it satisfies all the conditions. It satisfies this condition and satisfies that condition. So for example, in our example, what would be R intersection G? That would be things that are both red and green. So part of P1, P2, and also part of P2, P3, that's exactly P2. So if you selected R intersection G, that would be cutting up only this one pepper. That is not the one that I was instructed to cut up. You could, this is a good life lesson for you. You could, if you cut up the red and the green pepper, you could then get into an argument with your wife about did you cut up the right peppers? Because this is slightly ambiguous, right? But I think what they meant is cut all of them up. So it is true, English language is sometimes ambiguous, but in this case I think we mean R union G. By the way, this is exactly one of the homework problems. One of the homework problems has this exact pictures of peppers, and it's like, hey, how do you express the yellow pepper in terms of these sets, things like that. Okay, questions or comments about the warm-up problem? Okay, on Monday's class, we left you with another problem in MathMatize. Let's see if I can find that. That would be here, and I have to bring it over so you can see it. Okay. You might wonder, why do I have a pyramid? We'll get to the pyramid in a few minutes. But we're going to start with this problem that we left off with on Monday's class, which is a red dice and a blue dice are tossed. Define the following two events. Event A, the red dice shows an even number, and event B, the sum of the dice is 4 or less. And these were the answers. So at last class we left before we revealed them, but it seems like most people picked 1 out of 18. Pretty sizable chunk picked 1 out of 12. I'm going to go over it and show you the right answer. But let me start with some comments. So the first comment is if you were to calculate these things individually, which I think we did in that class, then the probability of an even number, which I'll write like this, probability of even number on red, I'll call it even on red. We're going to go over this notation some more, but this is a funny P that stands for probability. If you calculate that on its own, it's a half. And if you calculate this one on its own, the probability the sum is 4 or less. I think we did that last class, and that is 1/6. And it's very tempting when you have two numbers like this to sort of combine them. How could you combine a half and a sixth? Well, you can multiply them. And so you could do a 12th is a half times a sixth. And this is a common mistake. So don't do this. This is the wrong answer. This is wrong. Let's do this. Let's put wrong. So this is the danger of talking about things that are wrong in class, is after the class, people will always tell you, when you multiplied them, that's what I was doing on my homework. I'm like, no, I was trying to tell you, don't do that. So if you multiplied them in this problem, that is not the right answer. And this is a common misconception. So let me write down common mistake. And the mistake is that both events, right? And equals multiply. And that is not always true. The correct thing. Okay. So yeah. Okay. Let's box this so no one thinks that this is a true fact. This is false. 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 Don't get mixed up. Okay. The correct thing is that and equals intersection. Intersection. And we'll see later in the course that under special circumstances, an intersection in some miraculous situation does multiply. So this is not like completely wrong. It's just not exactly right. And this is what we want you to start with, that and equals intersection. So to do this problem, you cannot just do a half and a sixth. There is no way you will ever get the right answer with just a half and a sixth. What you have to do is you have to write out these two events, and then you have to do the intersection. That's what the question is doing. And to write out the two events, we had this nice grid over here, which let me see if I can make a copy of or move it. Okay. Will it let me move it? That's funny. Okay, perhaps we will leave it right over here. And we'll just do the problem right on top of this grid, and hopefully I don't need more grids later. Okay, so what are the two events? One event was that the red dice shows an even number. The red dice, is it red or is it blue? The red dice shows an even number. Okay, amazing. So you can highlight that and see what that is. Let's highlight that in orange. So the red dice being an even number are these things, this row, or that row. So that is what we would call event A. Event A. So an event is a collection of all these outcomes. In this case, it has 6, 12, 18 outcomes in it. And then event B is that the sum is less than 4. Okay, in our problem, the sum being less than 4, this is the kind of thing we talked about last class, corresponds to this little corner over here. So here the sum is 2, here the sum is 3, and here the sum is 4. So the sum has to be, 4 or less? The sum of the two dice is 4 or less. Okay, so there you go. So this event B. Okay, event B was that little corner. And then we need to do the intersection. The intersection is where do they overlap. That is what and means. Satisfying both conditions, it is these two. So this is A intersect B. The intersection is just those two things. And so finally, when someone says, please find the probability both things happen, then you're talking about the intersection. And in this case, the intersection has two things in it. There are 36 things total, and this was the rule we used last time. So therefore, you could write this as the probability of A intersect B, and that would be the number of things in A intersect B divided by the total number of things, and that is 2 out of 36 total, also known as 1 out of 18, which is the correct answer. And indeed, most people got that right. So I think most people were on the right page, but this is the sort of way I would calculate it out. If this was an exam problem, this is the kind of thing we would expect to see on your sheet. Any questions or comments about that problem? Yeah? That is a great question. I think I could see a question where we give you the grid, and then there's also some questions we'll ask you to do your own grid. That's right. And in fact, the rest of today's class is going to be a little bit about how do you get the grid. So, yeah.
So the other thing is, often because you can think out the grid, you don't actually need to recreate the entire grid in order to think of the solution.
That's right.
You can think of the points in one way and then select out those mentally very quickly.
Yeah, like an example would be of kind of doing a shortcut is instead of writing out the whole grid, is maybe you would say, okay, the whole grid, I know it has 36 things in it, and I know that the ones where it sums to 4 is this little corner. So you draw out just the corner, right? And then if you have the corner and you know that the total number of things is 36, you could get the problem, you could do the rest of the problem like that as a shortcut. But I think the way we did it here is the sort of the full way to do it, and then as you get more advanced, you can sort of skip some of the steps as you understand them. Great question. Anyone else? Okay.
I would add one more point.
Yes, please.
The formula of the equation at the bottom, number of
Yes.
things in A intersect B,
Yeah.
and the total number of things, is assuming
Yes.
in this case, equally
Right.
probable.
We are going to talk about this. This is what the picture of the pyramid is about. We'll get to it. Yes. This is a very, like, we did this without sort of justifying it, and we're going to talk more in detail about it next. Why is it that we did that? Great question. Okay. Anyone else? Okay. So let me now explain to you what is the point of the pyramid picture, which since I can't move the pyramid picture, it might be sort of oddly placed, but that'll be that. Okay. I want to go this way. Okay. So the thing we're going to talk about next, you've seen a problem and sort of like how to calculate the answer, but I'm going to try to answer the question, what are we even doing? What are we even doing? Okay, and this is what I think of like formalizing the problem-solving process into formal mathematics. And as you go into university, you'll do more and more of this stuff. You sort of go from like high school calculus, you're just sort of like solving problems, and then in university calculus, you learn like actual theorems. Like you learn the intermediate value theorem, the fundamental theorem of calculus, and you have like these formal proofs. And this is kind of going from kind of informal thinking to more formal thinking. And I wanted to use this analogy of the pyramid. So here's my analogy, which is the real world is sometimes kind of messy. Maybe I can draw a real world over here. So this is a real world, actual, honest to goodness pyramid. And it has some dimensions and so on. But if somebody said, please calculate the volume of this pyramid, you would first convert it into something a little bit more mathematical. So you start with the real world. Someone asks you a question that you want to answer in the real world, like what is the volume of this pyramid? And the first thing you do is you convert it into a math problem. So convert into math. Okay. And then you get some sort of like like some sort of math world where things are very nice and everything is perfect. And this is like the platonic world of math problems. Okay, so yeah, I have to picture it over here. I had in my mind drawing it sideways. And in our example, we had a problem about two dice rolled. Okay, and of course, two dice rolled is some physical object in the real world, but we don't deal with that object when we do probability class. We convert the real world into our math world, and that is this thing over here. So this is a real, quote, real probability problem. I'll use the word chance. It's a real problem about chance. And we convert that into our math world. The process of converting from the real world to the math world is sometimes called modeling. So what we are doing is some math modeling. And is modeling spelled with two L's? That seems wrong. That looks like yodeling to me. What do you think? It's good? Yes. Okay. Let's make it. Let's make it even more exciting. Modeling. Okay. Okay. Now I'm embarrassed by that. Let's erase modeling. So this process is called modeling, and I think a lot of times when you're in math class, you just start in the math world and you don't think about this stuff, but it is very important. And as you kind of go higher into math, different classes will talk about modeling more or less. The field of statistics is very closely tied to real world and cares a lot about this modeling process. So the connection between the real world and the math world is very important. In our particular case, we take a problem like this about the real world and we turn it into a probability problem. And the key thing, our platonic ideal of a probability problem, involves something called a probability space. A probability space. Mathematicians are pretty uncreative when it comes to names. So the thing that has probability in it is a probability space. If you take linear algebra class, what do they call the thing that has all the vectors in it? That's a vector space. What is the thing that has all the functions in it? It's a function space. But this is a specific mathematical definition, and it is like the stage on which we are going to solve the real world problem. So step one is to model the problem and turn it into a probability space. I'll tell you more about what a probability space is in just 1 second. But step two is to solve the problem in the probability space. So you sort of solve with math. That is step two. And that is exactly what we just did. So in the example we just did, step one was converting it into this grid, a problem about two dice, convert it into this grid. Step two was you think about events and intersections and things like that. You solve the problem in the probability space. And then step three is like you interpret back into the real world. So step three, interpret. And in this case, we would say, look, I calculated that the probability is 1 over 18. So that means the chances of rolling the two dice and having both event A and event B happen in our practice problem, it should happen about 1 out of every 18 times. So the interpretation in the real world is also part of the process. A lot of the class and a lot of your math classes, you spend all your time in step two, even though step one and step three are also important. But that really is because this step is somehow the most technical, and like you need the most specialized skills to do this step. But that is the sort of big picture. I'll tell you in a second what is a probability space and how, a little bit more about this conversion process. But any questions or comments so far? Yeah. Oh, well, because when someone says this problem, right? Like we didn't like weigh any dice or like measure any dice, right? And I think like sort of baked into our modeling process in our step one, we use assumptions. And the assumptions will often be based on the information you're given and what you have available to you and sort of the context the question is asking. So if you're in probability class and someone asks you this, it's very reasonable to assume that it satisfies this grid. If you're in geometry class and someone asks you about the Pyramid of Giza and what is the volume, very reasonable to assume it has a perfectly square base, and so on and so on. If you're in archaeology class and they ask you what is the volume of the Pyramid of Giza, they probably want you to look up like a book, right? So that's what I mean by real. The problems that we're doing, they do have a correspondence to real life, and as you get further and further into statistics, they become very useful in real life for real life things, like the Department of Statistics does all sorts of actual real problems that help clinical trials and stuff. In this class, they're going to be, I think, mostly problems that are real in quotes, like this one. Oh, I'm approaching my usage limit. Good to know. OK. Yeah, that's great. Great question. Any other questions or comments? Let's talk about what is a probability space. A probability space. So it has 3 ingredients. And you have already actually seen all the ingredients. We just haven't told you what they are. A probability space has 3 ingredients. So has 3 ingredients. So we've already sort of told you these sort of informally, but let's do them a bit more formally. The first one is the sample space. The sample space that is sometimes denoted with S or with omega. This is the very first one on the little dictionary that I posted online for you guys. And this is all the possible outcomes. All possible outcomes. I kind of like to think of this as like the multiverse of all the different ways the universe could unfold in our problem. When you roll 2 dice, the universe sort of splits into 36 possibilities, right? And in some of those possibilities, the dice all have different values. The sample space S, or also called the space omega, which is kind of a cool way to say the multiverse, is all the possible things that can happen. And the items are sometimes called outcomes or events. So sometimes we'll write E in S for some outcome, and we use a lowercase e. This little symbol means in, and that means this thing is an element of this set of possible outcomes. Sometimes people will write omega in capital omega. So this is a lowercase omega, and this is a capital omega. And that's saying we're in the universe, in this particular universe. Sometimes these are called simple outcomes. There's another word that I really like that has a slightly more specific meaning, but it is an atom. So it's an atom of the sample space. The sample space is a big collection of stuff, and it has these sort of indivisible pieces, the atoms that it is made out of. In our example, the sample space was this grid, all the possible combinations of 2 numbers, 1 to 6, and the atoms are these pairs of numbers. So like 1, 6 is one of the elements. 6, 4 is another one of the elements. There are 36 elements in total. Yes?
Wasn't that 2 more expressions for simple outcomes?
Yes,
and,
please.
Atom
Yeah.
is simple event.
Simple event, yes.
Event that can't be decomposed using that sample space and a point.
A point, yes. Oh, I like a point. That's very nice. A point. Yeah. So the one I would, all of these are great. The one that is a little bit scary, you should be slightly worried about, is simple event. And that is because event already means something else. And that is the next ingredient in the probability space, is the events. The events. Some people will write this with an F or a big E. Usually people, sometimes people don't write it at all. And this is all possible events. And what is an event? An event is a collection of outcomes. So more than one outcome put together is called an event. An event E, it is some set of possible outcomes. Let me not use the word possible. Let me say some specific outcomes we're talking about. And we put curly brackets around them to mean it is a set. A great example is the problem we just did. We had 2 events. We had the event A in orange and the event B in green, and they are 2 possible subsets of the whole space that is going on there. In sort of simple probability, the events are all the possible subsets. So I'll put a little bullet point with an asterisk. Sometimes it's all possible subsets of S. It turns out, if you're scared of scary things, then you must shut your ears for the next minute. It turns out if the event space, the sample space, is infinite, then you can't do all possible subsets. And there's some like weird technical things involving the axiom of choice and non-measurability and all sorts of crazy shenanigans. I'll put star equals things are more complicated if infinite. Things are more complicated. And I'm teaching a 4th year class next term on this kind of stuff, on infinite measure spaces. If S is infinite. But fortunately for us in this class, at least to start with, S will always be finite, and then so it really is all possible subsets, and you don't need to worry about this kind of thing. The events are all the possible subsets of S. Questions or comments about those two? Yeah. Yes, absolutely. Yeah. So sometimes you'll say, what is the probability of something happening? And the answer is, it's impossible, and then the probability will be 0. And it could just have 1. So for example, in the question we just did, it worked out to 2, but it could easily, if it was exactly 4, then it would have been just 1. Absolutely. There is a distinction in mathematics between the item. So for example, the item 2, 2 is, we think of that as the thing. It's just one thing, 2, 2. And the set containing 2, 2 is like a bag that holds one item. And the bag holding one item is the event, and the 2, 2 itself is the simple outcome. And we sort of mentally think of those as different types of objects, even though, of course, they're very similar. That is why it's dangerous to think of a simple event. I think is a scary word, because I would mix it up with event. An event is a collection of things, could potentially contain nothing, could potentially contain one thing, but a simple event is an item that goes in an event. So that's why it's a kind of a weird one. Yeah, great question. Anyone else? Yeah.
Regarding the question with the dice.
Yeah.
Wasn't the first dice at the outcome?
Yeah. Did I do the second dice?
Yeah, because wouldn't the line be diagonal instead of horizontal?
They would be vertical if it was the other dice. But let me see what it says. It says the red dice shows an even number, and in my thing I color coded it. So the red dice was the second number. No, I think it's a very important distinction. We're going to talk about this in a second. Why did I put the red dice second? That was a choice I made. And you could equally well have done the same problem, and when you would have had columns, and your answer would be perfectly correct as well, as long as you did everything else right. Okay. Yes. That's right. If it was the total roll, then it would be the diagonal. You'd have some diagonal stripes. Yeah, very good. Yeah. It should be. It might not be yet, in which case I will update. Okay, yeah, someone else is shaking their head. I will check and make sure that the link is live. Sometimes you put things on and it hides them by default. I will double check after the class and make sure you can see it. Yeah, fantastic. Yeah. Yes. Yes, absolutely, yeah. So, and I think what you're pointing out is when you do the process of going from the real world to the math world, you have a lot of choices in the modeling. And in the one we did, we chose the 36 outcomes that we sort of expect for the dice. If you were doing the same problem at a casino, maybe you want to include a situation where the dice falls off the table. Maybe that is relevant to what you're thinking about, and then you would want to include it. There's a really excellent quote that I really like, and it is the following. All models are wrong. All models are wrong. So whenever you do a math model, it will be wrong. The next part of the quote is also important, but some models are useful. Some models are useful. And this is a quote by Mr. Box. Maybe I should say Dr. Box. George Box, let's call him George Box. Who is a famous statistician. And also, the algorithm, when you make random numbers on a computer, they use the Box algorithm. So famous guy. And the point is that when you do this modeling process, you are definitely going to throw out some information about the real world. And what you want to do is make sure that the stuff you throw out is stuff that is OK to throw out. So something like landing in gum or something like that, maybe if you don't care about that, it's OK to throw it out. The same way you might be OK with the approximation of the real pyramid by a math pyramid. And that's fine. Yeah, great question. OK, so speaking of modeling, so far we've talked about the probability space. And indeed, the probability space, part of the modeling is the probability space. But I think most of the modeling is in the third ingredient, which is the probability. The probability. And I'm gonna write down the probability function. The probability function. And so I did my PhD sort of in probability theory, and it was very important in my field that you write P like this. So this is a blackboard bold P. That's what this is called. You might have seen a blackboard bold R before. It looks like that. Those are the real numbers. This is how you do bold letters on a chalkboard. And the reason we write this and we don't write just an uppercase p or a lowercase p is to remind us that this thing is a function. So this thing, it inputs events. So you'd write p of some event, and then it outputs a number. Let's say a number between 0 and 1. So that's why it's a function. Let me erase r. We're not doing r today. So it's the probability function. Why is it a function? It inputs things from here, the events, and it outputs numbers between 0 and 1. And not only that, it has to satisfy the so-called axioms of probability. The axioms of probability. Let's say the axioms of p. So these are the things that the p function must satisfy. And the first one I wrote over here. So number 1, the must be between 0 and 1. 0 and 1. And I'll say inclusive. So it could be equal to 0, it could be equal to 1. If you have negative numbers, that is not probability, that is something else. In quantum physics, you can have things that are complex, and then you square them in a certain way to get the probability. But the probability is always between 0 and 1. That is the first axiom. The second axiom is that disjoint things add. So this is an important axiom, disjoint. Actually, let me do that as the third axiom. That one's the most complicated one. Let me do the simpler axiom first, which is that the entire space is 100%. So the probability of something happening, the entire sample space S, that is 1. So the chance that something in your sample space happens always has to be 100%. You cannot have part of the sample space only add up to 50% or something. That would not be a proper probability space. And this is used all the time. This is sometimes called normalization, and is used all the time to do calculations. Okay, that one's pretty simple. The last one is maybe the interesting one, is disjoint events add. Disjoint, they add probabilities. Okay, so if you do the probability of A union B, that will be the probability of A plus the probability of B, but this is only true if A and B are disjoint. And that is the last axiom of probability. In a picture, if you kind of imagine the entire sample space as a big rectangle, this is saying if you have the probability of some blob over here, and you have the probability of a different blob over here, and you say, what is the probability that this one happens or this one happens? Well, you just add the two numbers. So this is a very simple thing. With these three axioms, you can come up with all sorts of wild and wacky different ways to satisfy them. But the simplest possible way, and this is sort of the most common example of a probability function, the simplest way, which is exactly what we did. The probability of some event E is equal to the number of things in E, E divided by the number of things in S. So this is the sort of equally likely situation where to get the probability of something, you just count the number of ways it can happen divided by the total number of things. This satisfies all the three axioms of probability. So is it always between 0 and 1? Well, E is always a subset of S. So the most this could be is 1, and the least it could be the least number of things you can have is 0. So that works. Is the probability of S equal to 1? Well, if you put S, you get the number of things in S divided by the number of things in S. The second axiom is satisfied. And disjoint events add because when you count the number of things in disjoint sets, it adds. So the number of things in A or B is the number of things in A plus the number of things in B, and therefore this formula works. So this is the way we're going to start the course with, and as we get more complicated, we'll do more complicated ones. In particular, soon we'll have something called probability trees. That's coming up soon. And that's another way to represent the probability space that we'll learn soon. But for now, we are doing this counting way, probability trees. Okay.
Again, that is emphasizing that the points are equally probable.
Yes. So when you do this the simplest way, the points are equally probable. And this is part of the modeling. So when you take a real-world problem and you model it and you turn it into a probability space and you assign it the probability function, which is the equally likely, you would hope that that corresponds to the real world. And in fact, I have a MathMatize question exactly about this issue that I will have you guys run through as a great example of this kind of issue. Let's see if I can find it. Here we go. Spinners. This is called spinners versus coins. And so in this problem, I have two situations that I want you to math model and come up with the probabilities. And in the first situation, we have a spinner wheel. Here's a picture of it with 3 equally sized segments labeled 0, 1, or 2. The spinner is spun to choose one of the 3 segments. The possible outcomes are 0, 1, 2. So I'm giving you a little hint here. When I say the possible outcomes are 0, 1, 2, I'm saying this is the probability space I'm thinking of, 0, 1, 2. True or false, the probability of landing on a 2 is equal to a third. And then in question 2, 2 coins are flipped. The number of heads is counted. The possible outcomes are 0, 1, and 2. True or false, the probability of getting 2 heads is also equal to 1/3. So I will let you think about that situation. You have to model these 2 situations, doing the spinner or doing the coins, and think about in your model what is the probability. Okay, let me give you, say, 2 minutes. Feel free to talk to your neighbors on this one. It's a good conceptual one. So let's see what you guys said. So we have the spinner, and we have the coins, and we're asking you to model these 2 situations and calculate the probability, and let's see what you guys said. So let's reveal counts. In the first one, for a score of 68 to 2, people said true, and I also believe it's true. So in question 1, I think it's unquestionably true. The chance of getting a 2 should be 1/3, the chance of getting a 0 should be a third, and the chance of getting a 1 should be a third. The probability space that models these is exactly the one we were talking about with the equally likely. You have 3 outcomes. Each outcome has a 1/3 chance. If you want to say something like, what is the chance of having a 0 or a 1, you would add the 2 probabilities. A third plus a third is 2/3, and so on. Seems like you guys are on the same page. The one that is interesting over here, and this is the one that sort of led in the 1600s to a lot of confusion about probability, is that you have 3 outcomes. Does that mean the probability is a third for each of them? Let's find out what you guys said. Ooh, in this one, 58 to 12, we said false. And in this situation, I also agree with you. So you guys said true for the first one and false for the second one, and those are the right answers. But what is going on here? Like, why is it that this one works and it's true, and this one is false? And again, I think it has to do with how you model, take the real-life problem and convert it into a probability space. In this one, the 0, 1, and 2 are equally likely, and that corresponds to reality. And in this one, they are not. So when we go to our little, the thing I said, the simplest possible thing that works, and this is the equally likely way, equally likely outcomes, equally likely outcomes. When they are equally likely, you can use this rule. If the outcomes are all equally likely, then you have this nice counting rule. And a good example of that is the spinner. So the example, the outcomes, if S equals 0, 1, 2 for a symmetric spinner, then that is a great rule. Then equally likely rule is good. Okay, and I do want to emphasize, I think the reason, the mathematical way I would justify to somebody, why is it that the spinner has this equally likely rule? Why does that correspond to reality? It is, to me, it's the symmetry. This is the thing that is creating it. Whenever you have an equally likely rule, there is some kind of symmetry under the hood. So this is the secret sauce, symmetry. I'll write that in big words, in big letters, symmetry. So for the spinner, you have 0, 1, and 2, and we kind of know that all the angles on the spinner, when we give it a big spin, they should end up being symmetric. So the situation 0, 1, and 2, and the situation 1, 2, and 0, these should be the same. They are rotations of each other. So this is a rotation. And that is the symmetry I'm talking about. When you rotate it, you should not change the probabilities. And the symmetric model, where everything is equally likely, that is the only way that you can be symmetric. And that is why the spinner 0, 1, and 2, that works. On the other hand, the example, S equals 0, 1, and 2 with equally likely outcomes, is not a good model for 2 coin flips. A good model for 2 coin flips, or more specifically, the number of heads on 2 coin flips. And the reason is, when you flip 2 coin flips, there is no symmetry between the number of heads that come up. So the situation of getting tails, heads, let's do tails, tails. versus the situation of tails heads, or let me say it another way. Let's say the map from 0 coin flips came up heads, are heads, to 1 coin flip is heads. Right? These are two outcomes in our sample space, the 0 and the 1. These two are not symmetric. There is no way to there's no reason to think that this should have the same probability of this. And the real reason is that this 1 coin flip is heads can happen in 2 ways. So the actual good model in this situation for 2 coin flips, a good model, is the kind of thing we've been doing with a grid. So the actual model you should do is this S, which has 4 things in it: heads, 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 tails, tails, heads, and tails, tails. And now we have symmetry. These 4 outcomes, they are all equally likely, and they do have a symmetry. The map between heads, heads, and tails, heads is, imagine at the mint where the coin was printed, that it was printed upside down. Then instead of being a heads, it would be a tails. So on any individual coin, there is a symmetry between heads and tails, and that's why our probability space should include all the possible things. Whereas there is no symmetry over here, and that is why this is a bad model. No symmetry. This one has yes symmetry. Okay. And that's why this is a good model. Okay. Any questions or comments about that? What was that? Yes, right. That's right. I'm taking the question and then we're going to stop. Okay. All right, we'll see you guys on Friday. Make sure you're aware of the homework that is now on MathMatize.